Quantum mechanics is funky in a kind of James Brown kind of way. Very, very funky. It's strange and counterintuitive.
Seth Lloyd runs the Center for Extreme Quantum Information Theory at MIT. It's sometimes hard to appreciate just how extreme this research can be.
Quantum computers are particularly fine for teasing out the subtle interactions between atoms and molecules and elementary particles, or for simulating what happens as a black hole collapses, or for that matter, a recent experiment that we did to actually implement a version of time travel. So you can use quantum computers for all kinds of exciting things.
And you can use the laws of quantum physics to create the ultimate way of sharing secrets.
Current codes that are used to send information securely over the internet are called public key codes, and they could be broken by a quantum computer. But quantum mechanics also supplies methods for communicating securely in a way that's guaranteed by the laws of physics. So these methods go under the name of quantum cryptography.
It's really a way of telling if someone is eavesdropping on your conversations. In the weird world of the very small, things can be in more than one place at once. But all that changes at the moment you actually look and measure where something is. It's known as the observer effect.
One of the basic principles about quantum mechanics is that when you look at something, you change it. And this simple feature allows you to communicate in a way that's provably secure.
But the reason it's useful is that this theory applies to a photon of light, which can be used to carry a message, a 1 or a 0. It means that if you are sending a quantum message, you can tell if someone else is observing it, if there is an eavesdropper on the line.
A good way to understand quantum cryptography is to think of 3 people, Alice, Bob, and Eve. Alice wants to send secret information to Bob, and Eve wants to listen in, to eavesdrop. Alice takes her information, a string of zeros and ones, or bits, and encodes them on photons, particles of light. Now, the encoding is done in such a way that Eve, if she looks at these photons, will inevitably mess them up. She'll change them in a way that Alice and Bob can figure out. So, after Alice has sent the photons to Bob, she and Bob can confer to find out which photons have been tampered with. The photons that haven't been tampered with, the pristine photons, now constitute a secret key shared only by Alice and Bob, whose security is guaranteed by the laws of physics.
Alice and Bob now have a secret code word, one they know no one had listened to, which they and only they know, and they can use this code word to send their messages. This system, using the behavior of some of the smallest particles in the universe, is already being used.
Quantum cryptography is already used by folks who want extreme security, by banks and by agencies whose job is to protect information. And nowadays there are a number of commercial companies that actually build quantum cryptographic systems, and for a fee, you too can communicate in complete and utter privacy guaranteed by the laws of quantum mechanics.